In this video, we are going to look into the properties of Z transform. So we would be defining a given property. If needed be, we will give a proof and also show some applications and examples of that property. So presently we have a linearity property, and it states that if we have x1 of n, which is multiplied by a coefficient a, and also we have x2 which is multiplied by a coefficient b. So as per the linearity property, we would have the transform of this function, which is x1 of z, and transform of x2, which is x2 of z, and they would be added together. So let us say that x1 of n is 1 by 2 power n u of n, and similarly we have x2 of n, which is simply 1 by 3 n u of n. Now both are right-sided sequences, and we are interested in finding the Z transform of x of n, which is x1 of n minus x2 of n. Now the Z transform of this from pair 5 in the pair table, so this is simply z over z minus 1 by 2, and for this we have absolute value of z greater than 1 by 2. And similarly, using the same pair, that is pair number 5 for this one, so we have z over z minus 1 by 3 with absolute value of z greater than 1 by 3. So independently, each one of them have an ROC which is outward of their respective pole. So 1 by 2 and it is outside. And similarly, for this one it is 1 by 3 and it is outward. But from the linearity property, it states that the intersection of R1 and R2 would be considered. Note that over here, if we combine the two ROCs, so we have a pole at 1 by 3 and then we have a pole at 1 by 2. Say this is our unit circle. So the intersection of R1 and R2 is available for the ROC which is outward of 1 by 2. So next we have time shifting property, and this states that for x of n we have a Z transform which is x of z, right? So if we give a time shift of n naught, so in that case again we would have x of z, but right now we will be multiplying with z raised to power minus n naught, that is constant value by which we are given a shift. So let us look into the proof of this property. So say this is our g of n, and we are interested in finding the Z transform of it. G of z is simply a summation g of n, that is x of n minus n naught z minus n. So right now this is not in a standard Z transform structure, so we can make use of the change in variable approach, such that the argument of x we need to convert it to a single variable. Here we denote that variable by literal m, and we say m is equal to n minus n naught. So when this summation would start from m minus infinity to infinity, because these values are infinity, so any constant would not make any change. So this would be x of m and z of minus. Now from here the n would be m plus n naught. We have m plus n naught. So note that the variable of summation is m, and we also have an n naught here, so we can take out this n naught because this is not a part of summation, so this would be simply z minus n naught x of m z minus m. But this right now is a standard definition of the Z transform, so this is simply x of z, and we have z minus n naught appearing over here. Hence this concludes the proof of time shifting property. To just cause some reflection on this property, we know that u of n has a Z transform which is z over z minus 1. But say we are shifting this by 2 units. That is, we are delaying it by 2 units, n minus 2. So in this case, from here we would have 1 over z square, z over z minus 1. In short, if we are delaying, so this means that we are adding poles. In the meanwhile, if we are advancing in time, so from here this would mean that we have z square multiplied by z over z minus 1. So this means that we are adding zeros. So for this to converge, ROC does not contain infinity. And for this to converge, ROC does not contain 0. So therefore, by looking into the delays or advance, we need to make appropriate changes for the ROC. The next property is scaling in the Z domain. So we are scaling in the Z domain, either expanding it or compressing it depending on the value of Z naught or alpha mentioned over here. Or from the time domain perspective, we are multiplying x of n with a coefficient to the power of n. So let us look into the proof of this property. Specifically, we are going to take this signal and say this is simply g of n. So g of z is z naught n x of n z minus n. Or we can simply say that x of n, and we can combine these two together. So we would have z over z naught raised to power n, and we have a summation. Now this is a standard transformation, that is a Z transformation, and we can write the Z transform, that is we have x of z by z naught, and this is actually appearing over here. So as an example, again say u of n is being considered, and this is simply z over z minus 1 with absolute value of z greater than 1. Now say this z naught of n, z naught of n is multiplied with u of n, and we are saying that z naught of n is equal to say 2. So in that case we have 2 power n u of n. So this would be simply z by 2 over z by 2 minus 1, or we can say z over z minus 2. But now the ROC would also be scaled as per this pole, so absolute value of z would be greater than 2. The next property is time reversal. That is, for x of n we have x of z. If we have x of minus n, then that would be having a transform x of 1 over z, or z inverse. For the proof, let us say that this is simply g of n. So its transform, that is g of z, is a summation x of minus n z minus n. But the argument of x right now is not in a standard form, so we need a change of variable. So say we set m, which is equal to minus n. So in this case we would have x of m z of plus m. So this n would change to plus m. Similarly, the limits of integration would be now reversed, so this will become plus infinity and this will become minus infinity. So in summation, if you are adding from plus infinity to minus infinity or minus infinity to plus infinity, it is the same, so it will not have any effect. So we can simply revert back, that is m minus infinity to infinity, and then we have x of m. But the standard form of Z transform has the variable of summation in a negative form. So z would be minus 1 minus m. Now this is having a canonical structure of the Z transform, so we can write it as x1 by z, or simply xz inverse, which is mentioned over here. Now again, let us take this example, that is 2 and u of n. So we have 2 and u of n. This has a transform which is z over z minus 2, and absolute value of z is greater than 2. Now if we reverse the time, that is, we say we are interested in 2 raised to power minus n u of minus n. So in this way, using this property, we would have 1 by z over 1 by z minus 2. And similarly, the ROC would be 1 by z, which is greater than 2. Absolute value of z, now this would be inverted because this would go over there and this can come back over here, so it would be 1 by 2. It would be less than 1 by 2. At the same time, the algebraic expression can be simplified by multiplying and dividing by z, so this would be 1 over 1 minus 2z. So we have an inverted OR in the ROC, which is expressed over here, and the algebraic expression is mentioned over here. Now let us move towards the convolution property, and it states that x1 of n is convolved with x2 of n in time domain. So if in time domain it is convolved, then in the z domain it is being multiplied. So we have a fairly simple operator in the z domain as compared to the time domain. So in order to prove this, let us say we have y of n, which is equivalent to x1 of n convolved with y2 of n. And we need to take the z transform of y of n. So that is, we are interested in y of z. So this would be equivalent to a summation n minus infinity to infinity y of n z of minus n, where y of n is simply x1 of n convolved with x2 of n, and this is x of k, that is x1 of k, x2 of n minus k, where k is from minus infinity to infinity. So this is the convolution sum operation. So plugging this in the first equality, we would have a double summation. The first summation is with respect to n, and the second summation is with respect to k. We have x1 of k, x2 of n minus k, and z of minus n. We can bring this summation out and this summation inward, and this would be over here, that is x1 of k, because it is dependent on k, and we would be left with the second summation, that is the outer summation, which is n minus infinity to infinity, and x2 n minus k is dependent on n, so this would be over here, and also z is dependent on n. Now to solve this argument, we say we have m which is equal to n minus k. Yes, we would have x of m. Also this n would change to m plus k, so we would have minus m and minus k. So this is the summation with respect to m, minus infinity to infinity, and over here we have x1 of k. But again, this k is not a variable of this summation, so we can extract it out of this summation. So this would be x1 of k, z minus k, and m minus infinity to infinity x of m z minus m. The first summation is with respect to k. This can be expressed as simply, note that this is x2, so this can be expressed as x2 of z, and this would be expressed as x1 of z. So they are being multiplied in the z domain, which is mentioned over here. So the next property is the first difference, and its proof is quite straightforward. Let us first define that if we have x of n and we are subtracting x of n minus 1 from it, so the z transform would be x of z and the coefficient would be 1 minus z inverse. Now using simply linearity property, and shifting in time, we can achieve this. That is, this would simply be x of z, and from shifting in time property, we have z inverse x of z, and then if we can take the common x of z, we would reach here. Now let us move towards the accumulation property, and we have y of n. I'm just going to write it over here. So this is simply a summation k minus infinity to n x of k, and the definition states that it has a z transform as 1 over z inverse x of z. Let us move towards the formal proof of this property, that is the accumulation property. So from the first equality we can write a generic form, that is we have k minus infinity to infinity. Now this n is changed to infinity, so this will be x of k u of n minus k. So why is it possible? This is because unit step function u of n minus k, this would either be 0 or 1, because unit step function can have a value of 0 or a 1. It would be 0 when n minus k, this whole argument, is less than 0, and it would be 1 when n minus k is positive, greater than or equal to 0. This can also be expressed as k is less than or equal to n. Whereas from this definition of unit step function, if you subsume or absorb the unit step function in the limits of summation, we are going to achieve the first equality. But do note that the second equality is the standard definition of convolution. That is, we have a convolution of x of n, this signal with this signal, in time domain u of n. So actually our output y of n is a convolution of x of n with the unit step function u of n. But from the convolution property, y of z is simply x of z times the z transform of this, which is simply z over z minus 1. So hence this is actually expressed over here, and this formulates the proof. Do note that now we have a pole at plus 1, right? So hence the ROC would be changed accordingly. So next we have the differentiation in the z domain, or we can also equally say that we have a multiplication in the time domain, multiplication with respect to the time variable n. So if we have nx of n, the z transform of it is minus z d by dz x of z. Let us move towards the proof of this property. If this is y of n, so this is simply y of z. So let us write y of z again, that is minus z d by dz x of z. But this has a standard formulation, which is a summation n minus infinity to infinity x of n z of minus n, and we have a differentiation with respect to z. Now the differentiation is with respect to z, so this variable would be affected. So as we have minus z summation, this would reappear over here as n x of n, and the power would be decreased by a value of minus 1. And again we have a summation from minus infinity to infinity. Also note that since there is a minus here, so this will become plus. Next, this z multiplied with this z minus n minus 1, so the value of minus 1 would disappear with the plus 1. So we would have a summation n minus infinity to infinity n x of n z minus n. So this is our y of z. So as we can say that y of z is a transform of y of n, where this value is simply y of n. So this concludes our proof for the differentiation in the z domain or multiplication of n with the signal.